Thank you very much. I'm very happy to give a talk in this workshop. So it's about random walk. Give me a second. So I will talk about random walk range, and as I expected, most of the audience are not probabilists. This talk is quite expository in nature, and essentially it's a 30-minute introduction to my one of the latest result of mine with 3 colleagues. So let me recall what random walk was. The random walk, I will consider the random walk on a Euclidean lattice, it's ZD. You start from the origin. Wherever you start, it doesn't matter. So I start from the origin, and you choose the next step uniformly at random from your adjacent site. You have 2D possibilities. So you have 1 over 2D probability to go any directions on the lattice, and you continue. Then as a result, you get an infinite sequence of random vectors, which I will denote by Sn. This is what you learn in a major theoretic probability course in undergraduate, or maybe graduate, depending on where you're from. And for this random vector, you know a lot. Actually, you can prove that it has 0 velocity. If you scale it by 1 over n, then it converges to 0, almost surely. Almost surely means probability 1. And the right scaling turns out to be 1 over square root of n, and under this scaling it converges to Gaussian random variable. It's a bit sloppy way of writing it, but it is called central limit theorem. And moreover, if you introduce this time parameter here, it's just an integer part, then it is known as the Donska's invariance range proof, which states that as a process it converges to so-called Brownian motion, or for mathematicians it's a Wiener process, in the space of continuous functions. Okay, and you know much more. For example, if you really want to know what is a really right scale for Sn, if n goes to infinity, then it turns out to be square root of n times log n. It's called law of iterated logarithm. So far, so good. And I don't assume you are familiar with this kind of fine properties, but in this talk I will be more interested in the range of the random walk, which is this S0 to Sn, which is regarded as a subset of ZD. And more precisely, I will be interested in the cardinality of this set. And of course, this cardinality is not n because there are some redundancy. You come back to the same site several times, and then its cardinality decreases. And the behavior of this set depends heavily on the dimension. When dimension is 1, of course, it's just an interval between maximum and minimum of the range. And it is interesting to study the probability distribution of this max, which scales like square root of n, etc. But I will not go into that direction. So I will focus on dimension 2 and higher in this talk. And even in higher dimensions, there is some dimension dependency, which will be dictated by this probability. So let gamma d be a probability that random walk will never come back to the origin. And from 1920, by the result of Polya, it is known that gamma 2, in dimension 2, this probability is 0. And dimension 3 and higher, this probability is positive. It says that 2-dimensional random walk is recurrent and 3-dimensional, higher dimensional random walk are transient. And by using this constant, we can immediately state the law of large numbers for the random walk range. More precisely, the size of the random walk range, which is already proved in the 1950s by Dvoretsky and Elders. It states that when the random walk is transient, then actually this range grows linearly in n. And if you scale it by 1 over n, it converges to this non-return probability. It's not, I will not give you a proof, of course, but it's relatively easy to understand because there is a redundancy in this set. You will get effectively one newcomer when you visit one site, and you get one more point in the range when you visit that point for the last time. And that probability is given by that. So that is a very rough explanation. And it holds almost surely and also in probability in L1. So in particular, the expected value of the range also converges to that number. And in dimension 2, as I said, this gamma 2 is 0, and therefore you have to introduce another scaling. And that is actually given by log n divided by n. And under this scaling, this converges to pi. So it's a kind of law of large numbers, but obviously in two-dimensional case, it's not a result of sort of ergodic theorem because this is not a linear average. And also in dimension 3, this range of the random walk is not an additive functional. I mean, it's not additive, it's rather subadditive. So you have to do something a bit more than usual ergodic theorem. And that is the kind of contents of this Dobretsky-Erdős paper. So there is a kind of intrinsic interest in this random walk range from probabilistic point of view. And after this Dobretsky-Erdős work, or more precisely, there is a following work by Spitzer in 1960s, which connect random walk range to potential theory. People get excited. And there are many other results in the probabilistic direction. For example, center limit theorem, non-center limit theorem. And if you look at the expected value of this size, then you can get actually almost complete asymptotic expansions. But actually, I will not go into that direction because I'm not talking to probabilists. If you are a probabilist, you will be very happy with that limit in distribution type result. But if you're not, then sooner or later, I think you will get this kind of question. You have a law of large numbers, very fine asymptotic expansion, so what? And of course, it's a bit dangerous question in mathematics. But of course, if you choose the topic very carefully, then you can give a quite nice explanation. At least I can give you an explanation which I like a lot. But before going to that, I have to tell you, I have to give you one more bowling slide, which is just a continuum analog of the random walk range. Continuum analog of the random walk is, of course, the Brownian motion. But the range of the Brownian motion has a measure 0. This is not easy to prove, but you can prove it if you are educated enough. So if you look at the measure of Brownian motion range, then it doesn't make sense. So instead, let's consider this tubular neighborhood of the Brownian motion, which somehow Mark Katz called Wiener sausage. Obviously, it's a nasty joke by Mark Katz, because if you Google Wiener sausage, you will find something completely different. Which makes it a bit difficult to do a research on Wiener sausage if you want to look for literature. But anyway, this is called Wiener sausage. It's just our neighborhood of Brownian path up to time t. And the theorem of Dobretsky and Erdős extends to this case. You have law of large numbers in dimension 3 and higher, and in 2 dimension you have log t divided by t scaling, and you have slightly different constant here. And notably here, you will get something from potential theory. It's just the capacity of the ball. So already you see a little bit of connection to the analysis, at least. And there is another remark. In this continuum setting, you can introduce scaling, because Brownian motion is scaling invariant stochastic process. So if you introduce the scaling, then you can restate this. I will focus on that. In this law of large numbers, if you do Brownian scaling, then you can translate this result in terms of r goes to 0 asymptotics. So you fix the length of the Brownian motion and you make it thinner and thinner. I mean, tubular neighborhood smaller and smaller. Then again, with this r to the d minus 2 scaling, it converges to t times the capacity. And r to the d minus 2 is coming from Brownian scaling, but also you can understand that this as just a scaling of capacity. Capacity of the ball scales like r to the d minus 2. This will be important in my explanation for so what. So here is the law of large numbers as Wiener sausage getting thinner and thinner. And this is somehow related to funny analysis question, which is called crash size problem. This is one of my favorite mathematical problems due to Mark Katz. So Katz proposed to consider the following problem. Consider the heat equation in a randomly perforated domain. So here is a square, which you can regard as a cocktail glass. You have a cocktail glass, and there are some ice inside, which means that you are considering heat equation with Dirichlet boundary condition, 0 boundary condition on the surface of this ice. And it's natural to impose Neumann boundary condition here, but it doesn't matter. Actually, Katz imposed the Dirichlet boundary condition. And everyone knows that if you crush the ice, then the cooling efficiency gets better. And the mathematical question is why and how. And to formulate this question, I put crushed ice, which is modeled by ball of radius epsilon, which later going to 0. And I put many number of balls, which will be denoted by capital N. And also, to make it more probabilistic, I assume that these crushed ice are uniformly distributed in the container, which is, of course, not very physically realistic, because if you put ice in the glass, then it's float. But anyway, you are drinking a cocktail in the space. Without gravity, then it's this situation. And the naive answer to this question is, it is because the surface area increases. And if this answer was correct, then I will not give you this example. So the answer is not correct. I mean, this is not the reason why the cooling efficiency increases.
Overlapping
is allowed, yes. That is another problem of this model. No, but actually, if you want to understand this behavior, what you should do is that you take epsilon goes to 0 and number n goes to infinity in such a way that the total surface area is preserved, right? And in that regime, actually the ice occupies only the vanishing volume fraction in this cocktail glass, and essentially you don't have any overlap. Okay, it depends on the dimension actually, but at least with high probability you don't have overlap. That is the regime we are interested in. And for this kind of problem, Katz gave a very nice formal argument using a Wiener sausage. And before explaining that, I have to recall what is called Katz formula. For any nice domain in RD, the solution to the heat equation starting from the uniform distribution can be written by using Brownian motion in this way. So the heat distribution at time t and x is nothing but probability for the Brownian motion starting from x never exit from this domain U. It's a baby, I mean, it's a very special case of something called Feynman-Katz formula, but in this case, I think it's called Katz formula. Now let's use this description. We are interested in this domain. There is a square of unit volume and balls, tiny balls are missing. And let's start looking at the expected value of this solution to the heat equation. This is a random variable because this domain is random. And this expectation corresponds to the uniform distribution over these balls. And then, of course, by using this Katz formula, you can write it in this way. And now I use Houdini. It's a very nice tool. I exchange the order of integration. Then, actually, these two are the same events, but it's natural to regard it in this way. So at the beginning, if you look at this event under the Wiener measure, then of course you have balls first and you put a Brownian path. And what you do is you ask a Brownian motion to avoid balls. But after using Houdini, it's more natural to put Brownian path first. There is a Brownian path. And you press the point in such a way that you don't hit the tubular neighborhood of the Brownian path. It's equivalent, but it's a matter of interpretation. Now, with this interpretation, what happens is that you have a container, but Wiener sausage is missing. And therefore, you have to put a point in the space which have this volume. And you have n points, and therefore this probability is exactly equal to that. And then if n goes to infinity, then you can write it as an exponential. Now, if you recall that this Wt epsilon, the volume of Wiener sausage behaves like epsilon to the d minus 2, this expectation varies in non-trivial way only if this number n is comparable to epsilon to the 2 minus d. I mean, if this guy depends non-trivial way, then this heat has a kind of non-trivial distribution between 0 and 1, which means that at fixed time t, heat decreases a little bit. So only if in this regime, cooling efficiency is bounded away from 0 and 1, which means that ice has non-trivial and measurable effect. And you should notice that in this regime, the total surface area, which is n times epsilon to the d minus 1, goes to 0. So indeed, the cooling efficiency increases if you crash size, but it is not because of surface area, but because of the capacity. And that is explained by this argument. And of course, this is only about the expected value. And if you want to make it with high probability statement or almost sure type statement, you have to compute the second moment, as usual in the week of large numbers. And you can do that. Well, actually, Katz didn't carry out all those mathematical details. And the first rigorous proof is given by Rauch and Taylor 1 year later. Well, Katz gave a talk in 1972, so it took 3 years maybe. But anyway, Rauch and Taylor gave a rigorous argument. Partly it's based on analytical techniques because they were not able to really compute second moment. And even later, Barry Simon presented a completely probabilistic argument in his book. That is very nice. Well, I forgot to mention, but Katz formulated that problem in terms of the eigenvalue. I mean, convergence of the eigenvalues. So up to this point, essentially the law of large numbers are done, and then Japanese mathematician Shin Ozawa proved a kind of central limit theorem for eigenvalues when the space dimension is less than or equal to 3. And he did it by largely analytic techniques, and that doesn't seem to extend readily to higher dimensions. And recently, I'm trying to do that with Mark Biskup in dimension 4 and higher. And it seems that it requires probabilistic techniques. But I don't think I have time to go into these details. And even more, there are much more followers from different contexts. For example, Khrushchev and Marchenko studied this kind of model from potential theoretic point of view. Figariolone, Papanikolaou, this is a homogenization. And Shiranescu-Murray, it is also homogenization. Scheber-Feldman did it on the Riemannian manifold, and so on.
And you don't mention Slittman here?
I don't think he wrote anything on crash size as a research paper. He included that in his monograph, and well, he used the idea of crash size in his research on what is coming in the next part, but it's not very direct. It's very much inspired, I think, but it's not. It's more implicit. Okay, this is the end of the first part. So you can use Wiener sausage to prove something not counterintuitive, but something I think interesting. Now I'm going into the second part of the talk. So essentially the first part of this talk was about small deviations of the Wiener sausage or random walk range. And now I'm going to switch to large deviations of the random walk range. But it is connected to something what we have already seen. Recall that we encountered the moment generating function of the Wiener sausage in the previous analysis. You remember that we evaluated the expected value of the heat equation, solution to the heat equation, and we end up with exponential to the volume of the Wiener sausage. But let me recall that in the discrete setting and also without Cocktail glass. Cocktail glass is outer boundary. Meaning that we put an obstacles on each side on the integer lattice with probability 1/2. You flip the coin on each side and you decide if you put an obstacle or not. And then you look at this probability. Random walk avoids obstacles up to some fixed time, and you take an expected value. This is what we have done. Then by using Fubini, this is equivalent to this event. No obstacles fall in the range of the random walk. Rn is a range. And in this setting, this precisely behaves like 2 to the minus cardinality of the range, of course. And you take an expected value you take an expected value with respect to the random walk. This is the moment generating function. Of course, I restricted the parameter 1/2, but of course you can replace this by arbitrary parameter between 0 and 1. And then it's really nothing but the moment generating function. And now here, somehow I'm interested in the behavior as n goes to infinity. In the last part, essentially we just looked at fixed n, and if it behaves like, no, it was continuous. Now I'm interested in the behavior as n goes to infinity, And this was studied by Donska and Baradan in 1970s, and the original motivation comes from the study of random Schrödinger operator of this form. And if you want to know some spectral behavior of the random Schrödinger operator, then you use some Abelian theorem to relate that to this kind of quantity. But I don't have enough time to go into this detail. This requires some prerequisites. Instead, I am interested in more probabilistic problem, which is the behavior of the random walk conditioned to avoid randomly located obstacles. There are obstacles, and once random walk hit it, then it will be killed. And I condition the random walk to avoid all those things, and I want to know how that affects the behavior of the random walk. Then, in that respect, this is nothing but the survival probability for the random walk up to time n. And if you know the asymptotics of the survival probability, maybe you can get some information about the survival strategy for the random walk. And mathematically, more precisely, I'm interested in this kind of Gibbs-like measure. So here is the survival probability. And under this survival event, I'm interested in the behavior of the random walk. But of course, this is not a probability measure, so I have to introduce this normalization. And this is obviously 0 over 0 limit. So in order to understand this measure, you naturally have to understand the behavior of the denominator first. And that is exactly this moment generating function. So there are a couple of motivations to study moment generating function. And this is done by Donska and Baradan in 1979. Actually, they did this for Wiener sausage 4 years before, 1975. And it took a bit of time to extend it to random walk, because actually this paper includes more general random walks, not only simple random walks. If it were only for simple random walks, it could be done by easier method, I think. But anyway, you look at this expected value. Now, from Dvoretsky and Erdős result, you know that almost surely this behaves like constant times n. Does it imply that this decays exponentially? It's not. This actually behaves like stretched exponentially. It decays much slower than typical speed. It's not surprising for probability people, but I don't know. They prove that this behaves like exponential minus constant times n to the d over d plus 2, and this constant, you can compute it, but much more important is that you have this variational expression. So it's an infimum of all open set of Rd, or volume times log 2 plus the first eigenvalue of minus Laplacian is minimized. And you can compute the value of this constant because due to this Faber-Cran isoperimetric inequality, this infimum is achieved by a ball. You can compute it up to first zero of zeros of the Bessel function. It is kind of interesting because Rn goes to infinity linearly in n, but it's stretched exponentially. And much more interesting, I think, is the method of proof. So how do they prove that? You look at this moment generating function, and because it's discrete, you can simply write it down as the sum over all possible shape of this random walk range. It's a huge sum, and usually you cannot expect to be able to compute this. But in this case, you are looking at n goes to infinity limit, and this is almost like range of random walk is contained in U. Then if you recall Katz's formula, it's a solution to the heat equation. And in long time, it behaves like exponential minus n times the first eigenvalue by the eigenfunction expansion. So this decays very fast in n, if U is small. If U is large, it's not so fast, but if U is small, then it decays very fast. On the other hand, if U is small, then this part is very large. But if U is large, then this part starts decaying. So it's essentially sum over the function, multiple of the function, both of them decays exponentially fast in different directions. And in such situation, it is at least vaguely known that there is something called Laplace Principle holds. which means that this huge sum is essentially supported by its maximal summand. And that can be proved in this setting. It requires huge theory of Donskoy-Bardhan, which is called large deviation principle. But anyway, by using that large deviation principle, Donskoy and Bardhan proved this Laplace principle. And after proving that, you can, apparently you have to take large U and you compute a little bit, then you can find the slight scaling, which is you put n to the 1 over d plus 2 in front of U, then you get this power and you end up with this variational problem. Okay. So large deviation principle is one of the methods to prove Laplace principle in the huge space, typically infinite dimensional space. And this is the first application of large deviation principle. And also from our point of view, we are interested in the behavior of the surviving random walk. And from that respect, this proof indicates that there is a best strategy, which is to stay in minimizer of this U, which we know that it is a ball. So the best strategy to stay in a ball of radius given by this dominates all the other strategies. Which means that if you condition the random walk to survive in obstacles, then most likely the random walk follow this strategy. And that was proved more than 10 years later, group of people. So this indication was made rigorous in the following form. So for any dimension 2 and higher and any epsilon, there is a random center such that under this conditional measure, the range of random walk is completely contained in the ball of radius almost rho n. This probability goes to 1. And this is in fact a bit stronger than what Donskoy and Bardhan's arguments suggest in the following sense. Well, I cannot tell you the details, but the large deviation principle is not about the range of the random walk, but actually it's about the occupation time of the random walk. You look at the measure, well, maybe it's not a good idea to go into detail. I have not so much time. It's about empirical measure, and because of that, large deviation principle only tells us that random walk spends almost all the time in the ball. But spending almost all the time doesn't exclude a small excursion going out from the ball, and therefore it takes like 16 years from Donskoy-Bardhan's result to Schnittmann, and this is only for 2 dimensions, and it's later extended to dimension 3 and higher by Schnittmann's student. So the random walk is confined in the ball, and maybe it's natural to ask what happens for the other direction. And that was done by Bolthausen. Bolthausen is one of the person who proved this in 2-dimensional random walk setting. He actually proved the other direction of the inclusion because he needed that in his proof. So therefore, you have a ball which is almost completely filled by the random walk, and also random walk does not go outside. So the random walk range under this conditional measure really looks like a ball in 2 dimensions. And very recently, I worked with Jandin, Ronfen-Sun, and Chan Jishu, and we managed to prove it higher dimensions. And 5 months later, we saw another proof by Rafael Sarf on archive. So, okay, so far, and this is the last slide, essentially. So we know that range of random walk is contained in a very, very thin annulus. So it's like a droplet. Then maybe it's natural to consider the surface fluctuation of the random walk range. And for this direction, we don't know so much, but at least we know that the cardinality of the range is bounded from above by rho n to the d minus 1, which is natural, times log rho n to the a.
So just to mu n here is the annealed measure, right?
Yes, it's an annealed measure. Well, actually, I defined it in terms of random walk range, so there is no random median. But it's a good question because for this proof, Beresticki and Sarf really use that random walk range weighted measure. And in our paper, we are using this obstacles description. And in that way, we have more coins to flip. And I think it's really, at least at this point so far, we really need that random obstacle description to this boundary size result.
But anyway, for the quench measure, this would not be true.
It's completely different, yes.
They do something, they go far. Right?
Yeah, sure. So at least this means that boundary of the range of random walk has Hausdorff dimension d-1. And there are some recommended readings, and that's it. Thank you very much.